Hi everyone, welcome to my latest video. This is entitled The Basics of Solar. Over the past few weeks I've learnt a massive amount about solar, so that I can create my own off-grid solar panel system. This is a summary of everything I've learnt about it in the process. Apologies for the cold as well. So main points I'm going to cover in this small video about solar panels, on-grid and off-grid issues, charge controllers, battery banks, inverters, wiring, fuses and safety, efficiency, and calculating your need to be able to work out how many solar panels you would need to cover a certain amount of energy. So to start with, solar panel types. There are two main types. There are a few more other types, but there's monocrystalline and polycrystalline. Essentially, monocrystalline panels are more efficient, but they're also more expensive. I use polycrystalline and they do fine for me. Solar panels come in different sizes, different physical sizes. Some are slightly more efficient than others, and they have their own watt ratings. They're achieved by the volt and the amperage ratings. Voltages of your solar panels can be 12 volts, 24 volts, 36 volts, etc. Wiring. Solar panels can be wired in series or parallel. So if I had a 12 volt panel and another 12 volt panel and I wired them in series, in other words joined the positive of one to the negative of the other, that would make my panel system 24 volts, but the same amount of amperage. Whereas if you wire them the other way, if you wire the positive to the positive and the negative to the negative of both panels, that would double up the amperage but keep the voltage the same. Solar panel irradiation. Irradiation is basically the exposure to the sun's rays, and we want maximum exposure. We want the most exposure to the sun as possible so we can generate a lot of energy. So the tilt matters. At different times of the year the sun gets higher or lower. It's lower in the winter and higher in the summer, so we need the tilt to be able to accompany that and sort of work with it. The direction of the panel matters as well, because the sun rises in the east and sets in the west. So first thing in the morning, ideally you want it pointing one way, and last thing in the evening, or in the evening you want it pointing the other way. You don't have to do this. A lot of people keep them facing south, and my panels face southwest. They're fixed. But to get maximum exposure, you would angle them differently. The other thing to do with irradiation is the amount of sunlight you can get. There aren't any proper figures available because, of course, each day is different. But on average, in winter you probably get about 2 hours per day, and in summer you could get up to around about 6 hours a day. Like I said, these figures are not really set in stone, and they're different. Depending on the day, really. So, I mean, you may get a terrible day where you get no hours, but on average, this is what I go by. How to calculate what your panels can generate. It's roughly the watt rating of each panel multiplied by the amount of hours. So in winter, you could guess that the amount of hours you're going to get on an average day is about 2 hours. So if you've got a 200 watt panel and you're going to get 2 hours of sunlight, you're going to get 400 watts. Around about, you get 400 watts of energy. 200 watts multiplied by 2 hours, 400 watts. Because the solar panel ratings are based on an hour of good sunlight. On-grid versus off-grid. If you're on-grid, the energy produced is not stored. It's sent straight to the grid. But it's cheaper on equipment costs. You still rely on the grid to buy back energy. So on-grid, you supply the grid with energy when you're not using it, but then you need to buy it back later on, when you do need it, maybe in the night time. Off-grid is completely different. With off-grid, you store the energy. It's not sent to the grid. It says send there. It's not sent to the grid, but it's more expensive on equipment costs. Mainly, it's the battery costs. Technically, you do not have to rely on the grid to supply energy. You may still have to rely on the grid anyway. It depends on how much you produce. Charge controllers. A charge controller controls the charging of your batteries. So if you are off-grid, you're going to need a charge controller. This prevents overcharge and helps your batteries to last longer, basically. There are two types of charge controllers. There's PWM and MPPT. PWM charge controllers are a set voltage, so you may get a PWM 12 volt charger, which is designed to have inputs of 12 volts and outputs of 12 volts. In other words, a 12 volt battery bank. If you don't keep the voltages the same with PWM, it won't work correctly. Excuse me. MPPT is maximum power point tracking. It's quite a clever technology which can allow different inputs and one set output. So you could have a 12 volt input and a 24 volt output, or you could have a 36 volt input and a 24 volt output. It doesn't really matter. Whatever happens, the MPPT charger steps the voltage down to work with whatever battery bank voltage you've got, and that's quite clever. So it could also make the most of extra voltage, whereas PWM wouldn't be able to. So they're a lot more efficient, but they're also a lot more expensive. I think you could probably get a PWM charger for around about 20 quid, whereas MPPT probably I'd say at least 100 quid. There are a lot of fake MPPTs on eBay, I've realised. Charge controllers are sold by amperage rating. You can get a 20 amp charge controller, 40 amp charge controller, etc. I can explain more about that later on. Overly high amperage requires thicker components and therefore more expensive. So the higher amperage ones have got bigger components in, so they're more expensive. If you get a charge controller that has a too low amperage rating, it'll overheat and damage the unit. They're not designed to handle so much current, so you have to get the correct one for your setup. Battery banks. Battery banks store your energy, again assuming that you're off-grid. You need a bank voltage, usually 12, 24, 36 or 48 volts. Usually we wouldn't go over 48 volts. The reason being is that current over 48 volts is considered to be dangerous to humans. If you got a shock from it over 48 volts, it's deemed as potentially life-threatening. So we stay under 50 volts. Higher voltage banks don't need to deliver as much current comparatively to other ones, and higher voltage and less current means thinner cables, so it's cheaper. Higher voltage also means less power loss over distance, and it saves energy. Going back to the higher voltage banks do not need to deliver as much current comparatively. The way that works is that if you need to deliver, say, 100 watts, to deliver 100 watts you'd need so much current with a 12 volt supply, but 100 watts at a 24 volt supply would need half of the current to be able to do that, and 48 needs half of the current of 24. So the higher the voltage, the less current you need, and that's why it's cheaper. That's why you don't need thick cables, because thinner cables would overheat. A battery bank can consist of one or more groups of batteries. In mine, for example, I have 12 batteries in groups of 6. So I have two 12 volt batteries wired together in series, and they have 6 of those banks wired in parallel. Each battery has 2 important ratings, voltage and amp hour, amp hour. Voltage is the pressure at which it can deliver current, and amp hour is the amount of current it can store. The higher the amp hour rating, the more energy you can store, and really, the higher the amp hour, probably the better the battery, really, as far as solar is concerned. Batteries can be wired up in series to increase the voltage, or parallel to increase the capacity. I've just touched on that. The main type of battery for solar is lead acid. I've not really seen any other ones used other than lead acid. Excuse me. Lead acid shouldn't be 100% discharged. The more you discharge the lead acid batteries, the more damage you do to them, providing you don't charge them back up very quickly. Lead acid batteries don't like to be left at a discharge rate because they start to sulfate. The recommended discharge is 0 to 20%. So if you have a battery that's rated at 100 amp hour, ideally you wouldn't discharge it to, you wouldn't take off more than 20 amp hours. So you wouldn't take off more than 20 amps for an hour, or the equivalent, because you could potentially do more damage if you didn't charge it up fast enough. Inverters. An inverter steps the voltage up from your battery bank to 220 to 240 volts. Obviously, your battery bank voltage, which will probably be 24 or something like that volts, isn't enough voltage to be able to power household devices. I mean, things like, a hairdryer or whatever, a PC, a TV, they expect you to deliver 220 to 240 volts. A 24 volt system wouldn't be able to do that. So you need to set the voltage up, and that's the job of the inverter. Inverters come with a rated voltage and 2 watt values, a continual watt rated and a peak watt rating. The continual watt rating is what it can continually deliver in energy, and the peak watt rating is what it can deliver at a spike, at a push if it needs to. Some devices use up a massive amount of energy to start up, and then they stabilise and take a continual lower amount of wattage. So this is why inverters have the 2 different ratings. Don't exceed the continual watt rating. Try not to exceed. The reason being is that it will start to overheat. Inverters need to be earthed at some point. If you've got a plug put into your inverter and you're drawing energy from your inverter, it needs to be earthed. By default, 12 and 24 volt systems are not earthed, but anything over 55 volts or something like that needs to be earthed. Wiring. So what goes where? The terminals from the solar panels go into the input of the charge controller, and then that energy from the charge controller then gets put into the batteries by the charge controller. The batteries and the bank are all wired together appropriately, depending on your setup. If you want a 12 volt system, generally speaking, you can just get 12 volt batteries and wire them all in parallel. If you want a 24 volt system, you're probably going to have to get banks of 2 12 volt batteries, wire them together in series, and then wire those individual banks in parallel. That depends on your system though, and what voltage you're trying to get. The inverter inputs are wired to the battery bank too, because it draws energy from the battery bank. The output of your inverter goes to whatever you're trying to run. Maybe it goes to an extension lead, maybe it goes directly into a device, I don't know, that's up to you. But it needs to be earthed. Cable thickness matters. The thickness in Britain is measured in millimetres squared. Higher currents require thicker cables. Cables which are too thin will heat up and waste energy. If they get too hot, it can become a fire hazard. So, if you're trying to draw a lot of current through cables, the cables need to be thick enough to be able to cope with that current. And if they're not thick enough, they can potentially burn up. Voltages and amperages matter when wiring up too. With PWM charge controller, all the components must be the same voltage. The charge controller and the wiring should be rated to handle more current than the system can supply. That's to try and avoid losses and build-up of heat. With MPPT, the voltages can be different. To save money on cabling, they can be wired up at a higher voltage than the battery bank. So, for example, in my system, my panels are wired up in series. So instead of them being 24 volts or 36 volts going into the charge controller, they're not. They're 36 volts multiplied by 4. I think it's about 144 volts. The reason I've done that is because the cables require less amperage. They don't need to be as thick, and there are less losses in higher voltages too. With MPPT, you can do that. You're allowed to do that, and it's okay. However, each part of the system in MPPT will need to work down on its own because voltages can be different. So the thickness of the cable on one side of their system may be different to the thicknesses of the wire on another side of the system. So each part needs to be assessed independently, and you have to decide for yourself how thick the wires need to be. Fuses and safety. Everything should be fused. In my panel system, everything is fused. Each battery bank is fused, and I've got MCBs, mixture circuit breakers in place, and anything in the 240 or 220 volt range also has an RCBO. Fuses can be useful. If you dropped a spanner on the batteries, for example, and it started arcing and sparking, after it draws a certain amount of current from the fuse, it will blow the fuse and therefore break the circuit and stop the flow of current. So it can potentially save problems. Maybe it could save a fire or overheating, battery blowing up, something like that. Again, earthing must be used. Inverters need to be linked to earth so that anything plugged in has an earth connection for safety. MCBs cut off when they detect a high current. These are useful for protecting devices and limiting unsafe amperages. If you know that your system shouldn't be able to deliver over a certain amount of current, you should put a MCB in place to stop that from happening, because batteries can be designed to let something draw a massive amount of current, and to not restrict the batteries, you could potentially let something draw a crazy amount of current which may do some damage or harm. So you should put an MCB in place, or in many places, where you know that current shouldn't exceed this amount of, the current shouldn't be over a certain amount. An RCD detects fluctuations in the current. This is important for higher voltages. This is when it detects some sort of problem between earth and neutral, and it cuts off if it does detect something. So if somebody touched the cable or something like that, hopefully it will cut off straight away so that nobody gets any dangerous shocks. Efficiency. There are efficiencies at every stage: the charge controller, batteries, the inverter, and you have to cater for all these losses. As a rough guide, you can cater for 30% loss. And I've got an example there. 100 watts comes in, charge controller loses 10%, 90 watts remaining. The battery loses another 9 watts, so 81 watts remaining. Inverter loses 8, and 73 watts remains. That's not entirely accurate, but it's just a guideline. Calculating your needs. All devices in your house should have markings which state the energy consumption. The watt rated is the maximum amount of watts used in 1 hour continuous use of that device. So your PC may say 200 watts in it. That's the amount of energy that it will use in 1 hour. If you add up the total amount of watt hours, you can find out roughly how much solar power you need to use. For example, your PC may be 150 watts for 4 hours a day, so that's 600 watt hours. Your light may be 20 watts for 4 hours a day, so that's 80 watt hours. Phone charge may be 5 watts for 8 hours a day, that's 40 watt hours. Add them all together, and that's 720 watt hours. To cater for loss, we'll multiply it by 1.5, in other words, add half of that value to itself. So that comes up with 1080 watt hours, and that's what you'll need to produce. So going back to the winter calculations before, assume that we have 2 hours of good sunlight a day, so 1080 watt hours divided by 2 means you need to generate 540 watt hours. 540 watts per hour. So you'd need panels rated at 540 watts. So panels are not usually sold at that sort of wattage, that's quite high, although I have seen 1 or 2. But divided by 3 gives a figure of 180 watts, so if you get 3 180 watts, that should do. Or alternatively, you could get two panels of 270 watts, which again you can get. And that's it. Thank you for watching my video, and I hope it's been useful. Thanks. Bye.